So we're going to perform a test to determine if the level of excitement before and after a roller coaster ride is the same. Well, clearly the claim is that they're not the same. One would simply mean, okay, excitement, and 10, you're absolutely thrilled. And as I mentioned, the claim is that they're not the same. So we asked 8 people, and we made it random by saying, okay, who skipped breakfast? 7, there is no bias. And these are the before values, and those are the after values, and they are dependent samples because I get the before and after values from the same individual. So the individual has a certain level of excitement, goes to the right, comes back, and how did the excitement change? Which makes the samples dependent. Of course, there are assumptions to this test. When you do the homework, it'll probably say, you know, this assumption is satisfied or that assumption is satisfied. But do pay attention to the assumptions, because eventually at the end of the semester, there is the concept of non-parametric statistics where assumptions don't matter. You can simply perform a test easily without assuming anything about the population. Okay. So, what type of test should we perform here? What is our typical hypothesis? The definition. We have a null and we have an alternative. You can look at your notes. Last time we used mu sub d. What is mu sub d? Or mu d? Go ahead, Sloan.
It's mu1 minus mu2.
And that is simply the average difference. We were very particular last time as to what before and after were, and we had to be careful because I believe last time we did a right tail test, or was it a left tail test? Left tail. So we had to be very cautious about what mu1 is, what mu2 is. I don't have to worry about that in this case because I'm saying it's not equal to, so it doesn't matter. But for the sake of it, we'll call mu1 to be before, mu2 to be after. The null is the average difference is equal to 0. The alternative, the average difference is not equal to 0. And the alternative is our claim. Step 2. Alpha is 0.1, which simply means the probability of we are setting a level for the probability of error in rejecting null under the assumed null, and that has to be 10% or below. So this is the upper bound that we seek. So if we get less than 0.1, it's good. What was step 3? Go ahead.
You take the before and after data, the MD, and you put it into the calculator.
But before we put in the, well, we can do it using the calculator, but last time I mentioned, it's pretty easy to find
the difference. Before and after difference.
the difference. So I'll just call that to be D. So for the first observation, it is 5 minus 10, which will give us negative 5. 4 minus 8, negative 4. 7 minus 10, negative 3. 6 minus 10, negative 4. 9 minus 10, negative 1. 7 minus 10, negative 3. 6 minus 9, negative 3. 6 minus 10, negative 4. And what do we need to find using those differences? The average and the standard deviation. What is the average difference?
Negative 3.375.
We'll call it negative 3.38, and the standard deviation,
1.187. 1.188.
we'll call it 1.19.
Sure.
So keep in mind, rounding does affect the conclusion in borderline cases, but I don't think that this is a borderline case. Step 4, we have to find the test statistic. The test statistic has a t-distribution. With degrees of freedom equals n minus 1. N here is 8. 8 minus 1 is 7. The formula for that is mu at d minus mu naught divided by s of d over square root of n. Mu naught is the value that is claimed in the null, and it's pretty obvious from our definition that mu naught is 0. In most cases, a test like this would tend to have mu naught to be 0. So we have the average of the differences, which is negative 3.38, divided by 1.19, over square root of 8. So here is the question. So of course I'm going to proceed with the test null, but if you have to take a guess, just by looking at the data, do you believe that we are going to reject the null? Or is it very likely that we will be rejecting the null?
It's fair.
Huh?
It's very likely that we will be rejecting them
Why?
because there clearly is like a difference. Like
Right.
there very clearly is.
So there are clear differences here, right? They're all negative. In a sense, the after level of excitement is greater than the before level of excitement for every single individual. So there seems to be a difference, and it is very likely. We just have to account for that standard deviation to address the conclusion from a statistical perspective. Does that make sense? Okay. What is the value of the test statistic? Negative 3.38. negative 5.
Negative 8.03.
Wow. Way up. 8.03.
03.
This is a two-tailed test, so the rejection region should be on which side? Both sides. What should the area be on each side?
One over 5.
0.25, in other words, alpha over 2. We are trying to find a critical value, so we have to use what function in the calculator? Inverse t. If your calculator doesn't have inverse t, what do? We make use of the chart or the table. So here, on the right hand side, this is t sub 1 minus alpha over 2, comma n minus 1. That would be 0.95, comma 7. On the left hand side, it is simply t alpha over 2, comma n minus 1. All we're trying to do is put the area below. The area below here is just alpha over 2. The area below that point is t, so what? It's 1 minus alpha over 2. So this would be t 0.05, 7. So you may either choose the right hand side to find the critical value, or the left hand side. It is entirely up to you. So inverse t 0.95, 7 in your calculator, and let's see what we get. So the critical value happens to be negative 1.895. Where is the test statistic? The test statistic was negative 8.03. So would it be here? Here? No. Way down somewhere here, because this is negative 1.895, so it's deep down in the rejection region. So, did the test statistic fall in the rejection region? Yes. Should we reject? No. Yes. Did we find evidence toward the claim? We rejected the null, so we're going to side with the alternative, which states that the difference is not equal to 0, the before and the after is not the same, so the claim is true. In the sense, we found evidence toward the claim. So I could simply say significant evidence toward claim. Even though I slip up occasionally, I'd say, oh, the alternative was true, but I immediately correct myself because we don't like to say the alternative is true, because if I said the alternative is true, no matter how many samples I collect, it'll always be the same conclusion. But that's not true. Based on the sample that we have significant evidence to support the claim. That makes sense? Okay. The next approach is the p-value approach. So this is a two-tailed test. So for a right-tailed test, we know the p-value is the area above the test statistic. For a left-tailed test, we know the p-value is below the test statistic. This is a two-tailed test, so what is the p-value? You should know this by now. 2 times the area above the think of gym, like workout for your abs.
The absolute value.
Thank you. The absolute value. Now you get it, absolute value. So what function should we use? Obviously not inverse t, because that gives us the critical value. TCDF. So 2 times. Zero is over there. That point happens to be 1.895. What is the absolute value of negative 8.03? Positive 8.03. And that is going to be right there. Here is a question. Even before you find that value, do we expect that number to be close to 1 or extremely small and close to 0? Extremely small, and it is going to be close to 0. Where does the area start? It starts at 8.03. Where does it end? E99. And what is the degrees of freedom? 7. Don't forget to multiply by 2. So the p-value is 8.9 times 10 raised to negative 5, which is 0.00009 approximately. And it's the same in percent, 0.009%. So based on the sample that we have and the null that we've defined, if we rejected the null, the probability that I could be wrong is 0.00009. That said, could I be confident enough to reject the null? Yes. That probability is close to 0. It is saying, okay, the chances that we are wrong is going to be very, very small. But yes?
Is the p-value supposed to be between 0 and 1?
Yes, it is a probability.
Oh, sorry, I totally ignored this
10 raised to
notation for
negative
half a
5.
second there.
You forgot that?
Yeah, I even wrote it down, I just slipped my hand.
Yeah, so that is something that's important. So oftentimes I have seen students forget about that term, the E negative 5 part. So keep in mind always the p-value is a probability and has to lie between 0 and 1. Good?
Yep.
So the test and interval, they're all related, but as I mentioned time and time again, that in numerical cases, we'd like to have an interval. So after the exam, we're going to do something called a goodness or fit test, which is for, there is a numerical case and there is a case for qualitative variables, and where it is not numerical. And a confidence interval may not make sense. So in this case, we can use either to come up with an interpretation or a conclusion about the claim. So the confidence interval for mu d is mu d hat plus e, the upper bounds, and mu d hat minus d. There is one thing for certain, after today, after this class, we'd all become moody. Very, very bad joke. How many of you got that? That could be you, okay. So, mu d hat plus e and mu d hat minus e. We know mu d hat, which is negative 3.38. What is e? Starts with the letter M.
The margin of error.
It is the margin of error. And the margin of error is always the product of two things, and what are the two things? Critical value and standard error. The standard error is always the denominator of the test statistic, theoretically. So in this case, it's simply SD over square root of n. And the critical value is t sub 1 minus alpha over 2, comma n minus 1. We already have the critical value because alpha is the same, 0.1. So 1 minus 0.1 over 2 is 0.95, comma 7. Multiplied by SD, 1.19, divided by square root of 8. So the critical value from earlier is 1.895. Let me know once you compute the value. So we have the margin of error, which is 0.8. We've got mu hat d, which is negative 3.38. So would be negative 3.38 minus 0.8 and negative 3.38 plus 0.8. and that would be negative 4.18, and this is 2.5. Yeah. So our 90% interval is way off from 0. 0 does not fall in that interval. So clearly we have mu1 minus mu2 to be less than 0. It cannot, there is no possibility based on the sample that it will become 0 because the entire interval is on that side. So that would imply mu1 is less than mu2. In other words, mu before is less than mu after, which is the same as saying that they're not the same. And by all means, the excitement level after the roller coaster ride is bigger than the excitement level before the roller coaster ride. Does that make sense? Good. Now do you see that when I said, when I've mentioned that multiple times that if 0 falls in the interval, then we cannot reject the norm. So clearly here 0 does not fall in the interval. In other words, the entire interval is to the left.